So to close out the 2021 MIT Digital Technology and Strategy Conference, we now have Professor Olivier de Weck, who is a professor of Aeronautics and Astronautics and Engineering Systems. And you will see in our program many of his other titles and roles. And his presentation is Improving Design Reuse Decisions Using Formal Models. Okay.
Okay, hello, welcome everyone. I think I'm the closing speaker, is that right, Carl? All right. I don't know if that's, that's an honor or, yes, it is an honor. Okay, thank you. I'm so excited to see all of you in person. In person, are you excited to be here? All right, yes. I can tell you that being back on campus, teaching, our students, speaking at conferences like these, gets me very excited. I think the human touch, I know this is the digital transformation conference, but I think let's not lose the human touch. And I think our students on campus are very excited to be back. We have a very rigorous protocol, with COVID. I got tested this morning. I'm negative. If you don't mind, I'll have my mask off, and so you can hear me better. And I'm really, really thrilled to see all of you. My topic today is around model-based system engineering, which is a big trend over the last few years. And specifically, the question addressed here is reuse of designs. This sounds great. We already have a lot of software. We have design physical systems. We have a library of assets in our company. We're just going to go reuse them and save a lot of money doing that. Well, maybe not. So the point of this talk is to share with you some of the highlights of a very, very recent doctoral thesis that was completed. So Dr. Alejandro Trujillo, Alex, this is his work. And so I just want to acknowledge that. He is now working at the Aerospace Corporation and applying this method that I'm going to share with you to large, particularly space systems. So a lot of the examples are in space, but I would ask you to stretch your imagination to see how this method might apply. If you're in, we have people here from oil and gas, right? We have automotive, we have software, we have medical devices. This method, I think, is quite universally applicable. And the key takeaway is that unless you really look into the details using a model-based system engineering approach, you may be either overestimating or underestimating how much value you can generate by reusing designs. That's the key point of this. So first of all, the word reuse is heavily overloaded. We use it all the time. And I think it's important to say, well, what is actually being reused? You can reuse the hardware, meaning you're going to use the same physical system over and over again. You probably recognize many of these things. SpaceX, the boosters that are being recovered. It's a very impressive feat, by the way. Lars Blackmore, who's the lead engineer at SpaceX, is a graduate of our department, who's really been the driving force behind making reusability of the first stage happen. The space shuttle was reusable. And so that's physical reuse. That's not quite where I'm going with this. Then what we have is reusing of design. So communication satellites on the lower left, those have been based on the product family approach. We're reusing the bus, we're using the design. And then finally, I'm going to talk about, and this is a planned reuse. This is a key point. Is the reuse planned? Did you think about it ahead of time, like in a product family? Or is the reuse unplanned? And when I say unplanned, I don't mean that's not a negative connotation. You just didn't design it with reuse in mind. Now you have the asset. Can I learn from it? Can I reuse it? And I think I'll show you on the Mars rovers. You see the family there, right? The Sojourner is the tiny little one, like microwave oven size. And then you've got Spirit and Opportunity. And then the latest rover, the MSL, Perseverance is quite large. And so you would be surprised how much reuse has happened in terms of knowledge, in terms of design, in terms of software, in terms of architectures between those generations of rovers. Now, One of the key questions you should ask is, whenever you're thinking about reusing a design or certain assets, is it right? Is it always good to reuse? And the answer is no. This is a very classic example of software reuse gone bad. Very famous case in the launch industry. Ariane 4, the European launcher out of Kourou, South America, French Guiana, was a very successful launch vehicle. The French developed the Ariane 5, which is still in use today. And basically it was a new design, but they reused bits and pieces of it, including the inertial reference code. And on the very first flight, this led to a major accident. Why did that happen? It happened because the ascent trajectory, the actual trajectory of the Ariane 5, is quite different from the Ariane 4. And in particular, it experiences more horizontal accelerations compared to the Ariane 4. And so the software for inertial guidance was basically reused one-to-one, but because the trajectory was different, the software reacted differently during the ascent. So when those high horizontal accelerations were experienced, the software was out of limits and stopped functioning. And basically, the rocket thought it was off course, Ariane 5, when it wasn't. And so a self-destruct was triggered, even though it was really unnecessary because there was no hardware failure at all. But it was caused by improper reuse of the software and improper evaluation of what would have to be done to that piece of software, including validation and testing to make the whole system successful. So when we think about characterizing legacy design reuse, part of this work was a survey of different practitioners in industry, and you can see the industry survey was done spring and summer of 2020, so about a year ago, and we had 149 responses from different industries. If you look at this, what it shows us is that in some industries, planned reuse is more common than in others, like automotive, for example, medical devices, hardware, software reuse, in defense as well. When it comes to space systems, which a lot of these are unprecedented systems, the ratio of unplanned reuse to planned reuse changes, and we see more unplanned reuse. So that's the intentionality of the reuse. Another question you should ask is, at what level, architectural level, does the reuse happen? Is it the full system, so satellite level, product level? Is it at the subsystem level, or is it component level reuse, like chips and processors and so forth? Then how much reuse? Is it copy as is? Sometimes people refer to this as cloning, right? We're going to clone the design, or we're going to reuse it but heavily modified. And then finally, when you're making the decision, we are going to reuse this piece or we're not going to reuse it, how are you making that decision? Is it sort of intuitive? Is it based on experience? Is it a structured method where you're going to go through some rigorous analysis? And as you can see here, as reuse is planned reuse is much more rigorous, unplanned reuse tends to be much more unstructured, and sometimes leads to not good outcomes, as I'll show you. Good. So what is model-based system engineering? This is, I think, a very good match with the topic of this conference, digital transformation. The traditional way that we do design, not just in aerospace, but in other industries, is shown on the left. Basically, we are maturing our design, whether that's computer-aided design, writing our software, our specifications, our requirements, and they are all scattered in different documents, right? Word documents, Excel is still a big tool that's used by engineers. And, yes, it's how we've done it for decades. People are familiar and comfortable with it, but there are huge problems with this. One is change propagation. You make a change in one part of the design, that change will not automatically propagate to the other parts of the design. So the new way of doing it is MBSE, Model-Based System Engineering, where the idea is that it's a fully digital design process. And there are different languages and tool environments to do this. I'm not endorsing any particular vendor or software or language, but one of them that we used in this work is called SysML, System Modeling Language. which was developed as a standard by the OMG, the Object Management Group, and there are many different instantiations of SysML. Fundamentally, at the heart of it, on the right, you have a database. It's a relational database that contains the single source of truth about your design. What are the part numbers? What parameters? What's the level of performance of your system? What is the cost of your system per unit? And then all of these supporting analyses, your bill of materials, it's all connected to that single source of truth. So if you make a change, then that change will propagate. If you're working with vendors and suppliers, they can also share in that database. That is how things should be done today. And I think we've turned the corner. I think 5 or 10 years ago, 80% were doing traditional engineering, and I think today we're really seeing a lot more model-based system engineering. And the other thing it allows you to do is digital twins, which I'm sure came up at this conference. So authoritative integrated models, multi-domain analysis, and model archiving and curation. So given that we have a model-based system engineering environment available to us, how do we now make the reuse decisions? And so the framework that was developed here is to take inputs, use a methodology and what we call the LDRM, the Legacy Design Reuse in MBSC approach, to produce outputs. And the output fundamentally is, at the end, should we reuse this design, this component, this subsystem, or should we just go with a from-scratch design? It helps you make that decision in a much more deliberate and better way. And we can show you statistically that it is better through some experiments that we've done, and I'm going to show you. So let me demonstrate first on a sample problem how this works. And the sample problem, I'm going to come back to our rovers, right? Our planetary exploration rovers. You saw those Mars rovers. And so the setting here is we're going back to the moon, right, with robots and humans. So we want to build a robotic lunar rover. And we want to potentially reuse as much as possible we can from our Mars rovers. Now, I'm looking at you guys. I don't know who's familiar with Mars versus Earth, but what are some of the big differences between the moon and Mars? There are really two major differences. Gravity. What's the gravity on Mars compared to Earth? 38%. So if we were standing on Mars right now, we would weigh 0.38 times the gravity we have here. And what's the gravity on the moon? 1/6, so about 15% roughly. So, there's a factor of 2 difference. So if you design something for Martian gravity, picking up rocks or whatever, that would probably be over-designed by a factor of 2 just from a gravity perspective for the moon. And then what's another big difference? Atmosphere. So Mars has an atmosphere. It's very thin. It's like 1% of Earth's atmosphere. It's CO2, 95% carbon dioxide. And the moon has essentially no atmosphere. So it's a very harsh thermal environment. So the thermal environment is much harsher. So from a gravity perspective, the moon is easier than Mars. But from a thermal perspective, the moon is more challenging than Mars. And so when you're thinking about reusing, and we're going to look at particularly the robotic arm, the arm system on the rover, you have differences in operating environment and then the requirements and the interfaces. And so we're going to use the MSL, the Mars Science Laboratory rover, as our starting point for reuse. So I know these are kind of eye charts. I apologize for that. I'm just going to try to keep it at a high level. But the diagram you see on the left is a meta model done in SysML that the different blocks are essentially the different parts of the analysis that you do to assess reuse. And so I'm just going to talk you through this quickly. You start with a mission description. So are you going to pick up rocks? Do you have a spectrometer at the end of the robotic arm? What's the reachability of the arm that you need to achieve? How do you decompose the system into its subsystems? So you see the arm is that little green box there on the right. And if we zoom into that, what are the interfaces with the software, with the power system, with the control system, maybe thermal management? Do you need to heat the arm? Do you need to heat parts of the arm so your actuators don't freeze, during the lunar night? Those are the kind of things you have to think about. Then legacy designs. What's actually available for reuse? You would think that's a trivial thing. You're in your company, you say, oh, we're designing a new car, we're designing a new medical device. Even what is the starting point? What are the reusable assets that we could begin that journey from? Really establishing that well is challenging. If the reuse is just, the information is only in the head of your employees or in a bunch of hard drives on laptops that are scattered throughout the world, that's not a good starting point. So what are the legacy designs? Specify the reuse need. So what do we actually need? This is the requirements. The list that you see on the right are the requirements that are imposed on the new system that you want to build. And so you can see there's a bunch of things here. There's the operating envelope of the robotic arm, the thermal limits. It's quite a bit, and you need to work through that. And I'm going to focus on the reachability, which I think is interesting and visual as well. And so we're working our way through the framework. We're looking at the reusable assets, the difference in requirements, and then eventually we need to assess rework. Like, can we just copy and paste this design, or would we have to modify it? And how much modification is needed and where? And so at this point, since this is the digital transformation conference, the question is, where are you going to do it? How are you going to do this analysis? And all of you have a different set of tools that you use. Some are in-house, some are from PLM providers. This is what we use just for this example of the robotic arm. So we're going to use MATLAB and Simulink on the left for our reachability analysis of the workspace. We're using SolidWorks for our CAD system, which is a parametrized model, and for our payload configuration. And then we're going to do our thermal environmental analysis in Excel, which is a classic sort of engineering tool. But the key is it's all tied together back to that SysML model, the system modeling language model, that keeps track of the interconnections between all these pieces of digital information. So what does that look like? So you see this is our robotic arm. We're keeping it very simple here. It has basically two elements and an end effector. You see the different angles that the arm can move, the lengths of your joints. And then this is what the analysis of just the reachability reveals. So in blue, we see the reachable boundary for the MSL arm. So this is the arm that we are inheriting from potentially. And the required workspace is shown in red. And then in green, we see the required workspace for the new design. And you see they do not line up perfectly. And so the modified, the point is that if we do not modify, if we just use the MSL robotic arm, we have reachability problems. We cannot satisfy the requirements. By modifying the arm, for example, shortening the upper arm by 10%, lengthening the forearm by 15%, and shortening the base by 15%, we can move from only 73% coverage to now 94% coverage, which we need for the new design. So this will tell us how much modification we need to do to that element for it to be satisfying our requirement, at least to 94% accuracy. And so this is kind of what it looks like. It is a simplified analysis. We acknowledge that, but it shows you the CAD model, the CSV file, the MATLAB analysis, and then all tying it back to that SysML model, which is our single source of truth. So that's our Luna technical analysis. So pandemic, we talked about the pandemic. How do you validate that this analysis is correct and how human designers would actually make decisions with and without this methodology? So what we came up with is Legos. Everybody, who likes Legos? Who's played with Legos in their childhood? Okay, I think about 80% of you. So here are basically different The original design is on the lower left. This is a kind of Lego version of it. And then on the right side of the chart, you see different solutions to the new requirements that people came up with. These are mainly students that we worked with, but some of them are mid-career people, so real engineers. So the with reuse design is on the top. And then some chose to say, oh, no, I'm not going to reuse any of this. I'm going to go completely from scratch, start a new from scratch design, and you see what they came up with at the bottom. So that's how we basically did it. And then what we did is we quantified for each participant in this trial, how much time did it take them? How many parts did they use in the design? You see the part count. You see the build time in minutes. So these are not like, 5 days. It's like 30 minutes, 20 minutes, 20 parts, 30 parts, and to find the amount of effort. And at the end of it, we could sort of, in the small sample, statistically say, well, was it worth it or was it not? So in this particular case, reuse is favored, but it's not super obvious. So the 33% time savings and then the number of modifications divided by the original parts is about 66%. So fundamentally, in the end, you have to say, is it worth to reuse or not? How much change do we have to make to the system? And what are the rework actions and changes to the WBS, the work breakdown structure, which you see at the bottom here. And so one of the other things we worry about, of course, is, well, how much rework effort is this? And there's a tool out there called CESUN. It was developed at the University of Southern California at USC. And it's a pretty widely used tool in industry for estimating how much system engineering effort is required. So we put this through CESUN to estimate, rework effort. So out of the method, you get, for example, then a list of all the rework actions you would have to take. Luna is our moon, so this is our lunar rover. And it gives you a very nice breakdown of all of the tasks that you have to do to turn that original Mars rover arm design into a functional Luna moon arm design that would satisfy requirements. And so at the end of it, we get a pretty detailed assessment of whether the reuse is worth it or not. So we have a rework campaign that we'd have to do, 3 minor gaps and 9 major gaps in the requirements. So that's the 24 rework actions. Fundamentally, the reuse of this robotic arm is feasible. We think it's feasible based on this. And then once you estimate the effort to do it, we would see about a 14% improvement with reuse. So it's not a slam dunk. It's not super obvious, but it looks like in this case, we would recommend the reuse of the Mars robotic arm to the lunar robotic arm with this set of rework actions. Reusability is feasible and a relatively realistic forecast of how much effort would be required. So validation, we went through a pretty, I think, rigorous validation procedure, both of the validity of the procedure itself as well as the results. I should also tell you that there is an interesting scale that NASA uses called the Reuse Readiness Level Scale. And it looks at these aspects: documentation, modularity. Professor Nick Roy, who spoke before me, talked about the importance of modularity. So is your design clearly modularized? Information compliance. How experienced is your staff? Is your staff of the right level of experience to actually do the reuse? How many of the original staff that were involved in the original design are still around? That's a big question. Right? So you could have great drawings and assets and software, but none of the original staff are still with you. That's a risk factor, right? And then verification and testing are the test reports, the analyses that were done during qualification of that piece. Are they still available or not? So you can map it against this reuse readiness level scale. Like I said, we went through this step-by-step validation of this reuse decision support process, and we found it to be quite convincing. I'm not going to go through all the details here, but I did mention the Lego environment. What's also interesting is beside the physical Legos, there's actually this thing, if you look in the upper left, it's called Lego Brick Studio, which is a digital design environment that is quite interesting. So we were able to do a lot of this remotely during the pandemic, comparing reuse designs versus from-scratch designs, and then getting our statistics about these 4 subsystems of the rover, the body and chassis, the suspension, the robotic arm, and the sensing mask, and having a truth model versus what people that did have this environment to help them make the decision would decide. And we think the correct reuse decisions were that the body and chassis should be designed from scratch based on these ratios of build time versus modification ratio. And the sensing mask should be done from scratch, but the suspension and the robotic arm should be reused, but with modification. So none of the 4 subsystems can be just cloned and reused as is without any changes based on this analysis. And so basically then we were able to quantify the benefit of using this method versus just doing it intuitively in terms of the build time estimates and the correctness of the reuse versus from scratch decision. And we found that on average across these subsystems, there was a 28% improvement in decision-making performance using model-based system engineering, which we thought was encouraging. So let me talk you briefly through 2 case studies before we go to the Q&A. The first case study was looking at the Aerocube program. The Aerocube program is a small satellite program that's been led by the Aerospace Corporation. This is a FFRDC, a nonprofit that supports mainly the Air Force and now the Space Force. They've been a leader in small satellite development for over 20 years. And so on the left side, you see here a program called the AC-10, the Aerocube 10. They're kind of twin, satellite A and B. And then there's a new program called Daily, which is also a remote sensing satellite. So the question is, does it make sense to reuse subsystems from the AC-10, the Aerocube 10, on the Daily mission? The good thing is for both of those, AC-10 and Daily, model-based system engineering exists. And we looked in particular at 4 subsystems. So the EPS is the electrical power system, CDH is command and data handling, communications, and then finally the ADCS, which is your attitude determination and pointing system. And so one of the challenges is, if you want to do model-based system engineering well, is to standardize the way that you document the design. So we had to do a little bit of translation or transformation of some of the models, but that was not too painful. And basically overlay the existing design versus the new design. And so what we found is that it's a mixed bag, as it is in many cases. If you compare the requirements, can you even compare the requirements between the old system and the new system? What about the interfaces? You see at the bottom here the battery, the body cells, this is the photovoltaic cells, the electrical power switch. All of those interfaces exist on the old design, but some of them do not. And so looking at model quality and consistency of your impacts and outputs, you can see the pairing of requirements. So does the requirement exist in the old system and the new system? The derived requirement pairs, and then how many unpaired requirements are there that are unique to the new system? So you can look at that, and you find that for the command and data handling system, which is your computers, onboard computers, and your communications, you can match those up pretty well. But for pointing and electrical power, it's a bit more challenging. Second case, so the takeaway from that first case was that the communications infrastructure and to some extent the command and data handling was almost identical. Those are the 2 subsystems you should reuse, but not the other 2. So my final case is the SLS, the Space Launch System. And I hope I'm not offending anybody working on this program right now with what I'm about to say. But this is basically the heavy lift launch vehicle that the US government has been working on and building with contractors to replace the space shuttle that retired 10 years ago in 2011. And what Congress did, so this is congressionally mandated reuse. Congress said, you will reuse two major parts of the space shuttle. The SRBs, which are the solid rocket boosters you see on the side, and the space shuttle main engines, which are the RS-25. So that was congressionally mandated. Was that, and it makes sense. We have these great engines, we have these solid rocket boosters, let's reuse them. Let's not go from scratch design. What our analysis shows that was probably the wrong decision. Basically, if you decompose the systems, you find that here's the RS-25, the main engine, but you know the engine has to be fed, right, with pressurized fuels. You have all these controls around the engine that reusing that engine but redesigning it for a completely different rocket caused so much rework and extra effort that the extra effort, because of the mandated reuse, ended up costing a lot more than if we had gone for a from-scratch design. And so our COSISMO analysis showed that the ratio, the design effort was about 42% higher. And the ratio, the cost driver multiplier with reuse, about 4.1 versus from scratch about 1.8, it's roughly a factor of 2. And one of the consequences of that complication of forcing the reuse has been that post the critical design review in 2014, you can see the blue line is the delays in the program. Early reuse locked in caused divergence and a lot of issues in integration and testing. So we don't think it was a good choice to mandate the reuse. And if we want to compare, for example, how much money has already been spent on SLS, about $18 billion versus the Starship design that's being developed by SpaceX from scratch with no mandated reuse. It's also expensive, right, 5 to 8 billion, but for a very similar class launch vehicle, we think that in this case, the reuse was not the right decision, and our analysis shows that that's in fact the case. I know that's controversial, but I think we can support our conclusions. So the final point is, if you want to design and model for reuse, from day one, you have to think about those things. Archiving your designs using standard patterns. Archiving also the design effort that you spent. Having a model-based system engineering archiving environment. Ensuring enterprise-wide accessibility of your design records while abiding in some industries by ITAR and export and security restrictions. Prevent obsolescence of old models. Adopting the usage of reusability metrics. And then finally, I think there's new job profiles. It's almost like a new type of jobs or professions that are coming out of this. A model curator. It's not a curator of a museum, but it's a curator of digital assets in a company. This is not a side job. This is something you need to do full-time and take very seriously. So, okay, I think this is my last chart because I think we have some discussion we want to have. What we've done here is develop a new approach to assess reuse decisions using a model-based system engineering environment. We've validated it, and we think that it leads to better decisions than we've traditionally done. And in general, I would say, people are too optimistic when it comes to the value of reuse. And I think this approach tempers that optimism and puts it on a more realistic basis. Okay, so I'll stop here and see if there's any questions. Yes. So which ones are we going for? Do you guys want to, do I pick them or? All right. All right, maybe I'll start with that one. Yeah, how well do MBSE practices tie to modern agile software development? That's a great question. So, agile development, I think, has been very successful in some types of software and increasingly in hardware systems too. But I think usually the starting point in agile development is from scratch, right? I think that's we just start from zero. We analyze our user stories, right? We come up with our sprints. We prioritize features that our customers would like. And then gradually we improve the design, we add features, which is really easy to do in software, but it's hard to do in hardware. So I will say that I think there's a bit of a disconnect between pure agile development, where you start from scratch as your default position, versus where you say, wow, we have hundreds of parts, we have millions of lines of software code that we've developed in our company for other products. Which of these could we reuse as a starting point of our next agile project? And so there's work to do on marrying up MBSE and software development, for sure. But it comes back to how visible are those assets as you begin a new project. Okay. Let's go to the next one. Is there a feedback loop back to the model in the MBS environment from, say, a satellite? I'm not sure what you mean by feedback loop, if you mean like a real-time feedback loop. But for sure, we're getting a lot of telemetry from our satellites today. So the amount of data, and this connects more with the IoT topic, right? We have a lot of sensors. So it does connect in the sense of digital twins. If you've done a really good job during model-based system engineering and development, you have a very detailed model of your system, not just its structure, but its computers, its sensors, the amount of data traffic that's happening on your system like a satellite. And it's a great initial condition for a digital twin. So after you launch your satellite, that telemetry shouldn't just be downloaded and looked at a screen and archived, but it should feed back and update your model. And if you do that well, you have your physical satellite in space, and then you have your digital twin, which, we talked about the Mars rovers. That's what JPL does. Every one of their rovers exists as a virtual version, and before a command is sent to the actual rover, move over to that rock and drill a hole into it, you do that on the digital twin of the rover to make sure that the commands that you're about to send are not going to cause some failure or some unexpected behavior. And as you do that, you improve the model, you improve its fidelity, you update parameters. Systems age and fail as well. You update that in the digital twin. So I think digital twin is the connection here. All right. Should we go to the next one? Okay. Have these formal end-to-end approaches been applied to software or network systems, for example, IT infrastructure? It's a little bit outside my area of expertise, to be honest with you, but I think one area where that is important and is being applied is in the area of cybersecurity. And so I know there are software environments that are able to, first of all, catalog all of your servers, create a map of them, which servers are up and running, which servers are disconnected from the network, which servers may have been compromised, and you should maybe isolate them. And so, yes, I think developing a digital model of both the physical infrastructure, the network, your databases, and then updating that as your systems are operating, as they're being upgraded, is really essential. And so I think in the world of IT software systems, particularly those systems that have to have very high uptime, you have to guarantee their air traffic control, for example. Those systems can't go down, or we just have to stop air traffic. Those systems are increasingly being modeled and managed using these digital environments. Yeah, and it's challenging. Okay, to what extent is a PLM software solution required to implement MBSE practices? So PLM stands for essentially product lifecycle management. And I would say it's essential. You can't do model-based system engineering without it. Again, I'm not endorsing any particular vendors but what's happened, I think, in the PLM industry is that we've had consolidation around maybe 3 or 4 different environments. And I'll just mention the ones that I'm familiar with. So you have the Dassault system. It's called the 3D experience around CATIA, SolidWorks, Simulia, and so forth. They are I think, very active in aerospace and the automotive industry. I think Boeing signed a $1 billion 10-year contract with Dassault Systèmes in 2017. Imagine that, $1 billion investment over 10 years in these digital tool environments. You can look it up. It's absolutely critical. And so there's a lot of different tools that are built around that particular suite. Then we have Siemens. I think Siemens is a very active player in PLM. I think Siemens is very strong in different industries like automotive or oil and gas. And then we have here in town PTC, right? PTC is a major PLM provider, and we know them quite well. And then, of course, the fourth one I want to mention is IBM. The whole IBM suite, the IBM Rational Suite. And so what we've seen is consolidation around these major clusters of tools and methods and tool chains. And some companies, like I spent 2 years at Airbus. I was on leave from MIT. I think at Airbus, we had all 4 of them. Like in Hamburg, you'd have Siemens, and then in France, you'd have... So inside the same company, you can have all of these PLM software solutions used in different product lines or divisions. And of course, that makes it really difficult to reuse digital assets, across business units and so forth. So that's really important. The other thing you're going to have to ask yourself is how much of this do we just use existing vendor tools out of the box, and how much do we do our own custom design solutions? And usually it's a mix. You'll find a mix of, we're going to use this CAD system, but we're going to use our own in-house bill of materials management system because we have, a different way of interacting with the suppliers. So it ends up being quite a complex, stitched together tapestry of tools and processes in the digital environment. And that's challenging and it's expensive. But the point is, if you don't do it, if you don't invest in it, you will be falling behind your competitors. Because in the end, it helps you be faster, make fewer mistakes, less rework, make better reuse decisions, which was, the point of this talk. Okay, you mentioned the congressionally mandated reuse. Was this not having sufficient information, falling for the sunk cost fallacy, something else? Yeah, I think it's all of that. If you were really honest about it, on these very large government programs, we're talking billion-dollar programs. There's also the, bringing the food back home to your district aspect. And so in some cases, congressionally mandated reuse is not so much a technical decision or a financial decision, but it's locking in contracts and workforce to particular congressional districts. It's just the truth of it. And if that's done too much, I think it's not a good use of taxpayer dollars. And what we've seen, I think, certainly in the space industry over the last decade is much more commercially driven, commercial resupply of the space station and buying these things as a service as opposed to buying the assets themselves. And that's not a bad thing. That's not a bad thing. Are there extensions of this design reuse modeling that may be applied to AI, ML reuse of models, training sets, and/or transfer learning? And I think, I just caught the last 2 minutes of Professor Nick Roy's comments, and I think I agree with him that reuse in machine learning is not really very advanced. Mostly, if you're applying a well-trained model to a completely different data set, you almost have to start training the model from scratch. There is one development that I think is very promising in machine learning, and I think it's called transfer learning. right? So you have a model that's trained well on a particular data set, and it's working well, it's performing well, but now you're going to apply it to a new situation. If that new situation is not too different from the original training data set, you can retrain the model, but you don't have to retrain it completely from zero. You can add a little bit of additional training data, maybe 10, 15, 20%, and do what's called transfer learning. And you'll converge quicker. And so I think transfer learning and machine learning is a good example of reuse or partial reuse. I don't know if that makes sense to some of you that are familiar with machine learning, but that would be my answer there. Can MBSE be applied to systems with emergent behaviors? Wow, okay. All systems have emergent behaviors, all of them. So emergent behavior is a functionality or a behavior of the system that you didn't predict that surprises you. Sometimes that's a good surprise. Oftentimes it's not, like a failure mode that you didn't expect. And so I would say that a good model-based system engineering environment will catch or predict some fraction of emergent behaviors that we would have missed traditionally in a non-digital environment, but not all of them. And I don't know what that percentage is, if it's half or 20% or 80%. I think it's context dependent. Okay, thank you. Thanks.